I'm going to present our poster, High Performance Computing Extension to the Frequency Domain Perfectly Matched Layer Method for phonon transport simulations. Most of this work was done by Rohit Kakadkar, a PhD student in my lab who recently graduated. He's now a software or a research software engineer at Brown University. I'm Joseph Patrick Fieser. I'm the PI at the University of Delaware, and the student currently working on this is Angira Chowdhury. Um, so let's start with what is the frequency domain perfectly matched layer method. So if you've never heard of this before, it's a new approach that we invented sometime around the year 2015 that we've been working on. So basically what it is a numerical analogy to how you would approach scattering problems analytically. What we do is we pretend like we have an incident plane wave that's going to impinge on some sort of impurity. So it could be like an embedded nanoparticle or whatever it is that you're interested in. Could be a nanoparticle, could be an interface, and you want to see how the phonon reflects off the interface, whatever it is. You prepare some sort of incident set of plane waves, one or more, and then you track how it interacts with the impurity. So either how it scatters off in all directions, or perhaps how it reflects or transmits across it if it's an interface. There's some to make this a computationally tractable problem. Basically, what we did was we take a similar approach to the atomistic Green's function formalism, where we only track harmonic interactions. And that has the benefit of creating a series of linear governing equations. And I'll talk a little bit more about that in a second. The response of the system always becomes, comes at the same frequency as the incident wave in that case. And the tricky part is how do you truncate the boundaries? Analytically, that's easy. Numerically, that's harder. We use a technique called the perfectly matched layers, thus the name. Basically, a perfectly matched layer is a method of absorbing wave energy at boundaries using a finite thickness layer of material. And it has the special property of the layer is that it has extremely low reflection coefficient, so that you can't basically tell. It absorbs, but it doesn't reflect, so you can't tell the difference between that and an infinite medium if you're sitting inside of your scatterer. So basically, the mathematical formalism involves using something called analytic continuation of the complex domain, but the bottom line is it works. You can either study scattering from, like enclosed geometries like nanoparticles, or you can use what we call the transmission geometry to send an incident wave across an interface and see how it either transmits or reflects across it. It's got some really nice numerical properties. All of the equations that come out of it are linear. The matrice that defines the operation is sparse, banded, and if you do it right, it's symmetric. There's no need to actually invert the matrix to solve the problem, unlike the atomistic Green's function formalism. You merely have to solve AX equal B. You would just need to solve it. You don't need to invert A. The perfectly matched layers turn out to mathematically be equivalent to dampers, which as a mechanical engineer appeals to me. It's easy to interpret the scattering results in that sense. So basically it just turns out that the scattered wave energy, or rate, is the rate of energy absorbed by dampers. And there's some really simple formulas to calculate the energy absorbed by dampers, just using linear response theory. We've used this to study a bunch of things so far, such as like how an interface, when it's roughened, begins to act diffuse, and in what sense it doesn't. So we've also studied scattering, mode by mode scattering from isolated nanoparticles. And more recently, we haven't published anything yet, but we're studying what happens when you try to transmit waves through nanoparticle composites. So presumably you'll see some, things like propagons, diffusons, and locons in these nanoparticle materials, and we can study larger arrays of material than I think anybody else at this point. So the point of this poster is to explore the parallelization techniques for this. And I'll just walk you through a couple of things that we know. So the good news is that, generally, if you want to calculate a transport property, you need to calculate an integral over all modes and all k-space, at least in the first Brillouin zone, or something equivalent to it. And the good news here is that, the way that we're doing our simulations mode by mode, each computation of the transmission coefficient or the scattering cross-section, or however you want to put it, is independent from one another, meaning that you can do all of the k's and all of the k vectors and all of the mode numbers at exactly the same time. You can submit them simultaneously on a parallel computer. So you can take what would normally be something like 40,000 simulations and do them on 200 cores in a little under 3 hours to calculate any particular transport property you want. So we've shown that. So if you go down to like reference, I guess 3, or either 2 or 3, we've shown some strategies for doing that previously, about maybe 2 years ago. More recently, we've been investigating how to actually do more than one mode and k vector at once. And the first most obvious strategy, since it turns out that any simulation at the same frequency will lead to the same characteristic matrix, A, is that what we can do is we've actually been able to lump all of the k vectors and modes that have the same frequency into the same simulation by just superposing the modes. It turns out that they're all linearly independent, and so you can do that. So you can take what would normally be like 40,000 simulations and simulate it in about 200 simulations, which are all, again, submitted at once. And so you can do another embarrassingly parallel simulation, set of simulations that reduces computation time by something like 1,000-fold, and then just post-process the frequency-dependent data. To go a step further, and this is really the cooler new thing that we've got, is that all of the frequency domain perfectly matched layer method mostly comes down to solving a sparse banded symmetric set of linear equations. And that's actually perfectly suited for iterative sparse solvers. So what we've done is we've implemented a Fortran-based MPI code based on the biconjugate gradient method that sets up and solves the frequency domain perfectly matched layer equations, taking force constants from density functional theory, and basically does that whole thing. Maybe I'll skip over the details a little bit, but basically it just separates the atoms into chunks of domains and only basically stores a finite number of rows of the characteristic matrix on a given processor. And it turns out that when you do that, because it's banded, and primarily because it's banded, there are only a few locations along the matrix where it actually needs to communicate while it's doing the biconjugate gradient method. Very, very few things need to be communicated. And so it can be efficiently done using the message passing interface. And we've shown so far, at least up to hundreds of processors, that we get almost linear speed up. So if this is something that interests you, you can learn more at any of the papers that are marked in the publications. We've also got an open source code available on GitHub right now. The link is directly below our timing graph here. And yeah, so there's 3 publications so far that are listed over on the right-hand side, plus a pair of them that will probably come out of the parallelization and the study of the nanoparticle composites. So you can see that over on the right-hand side. So the funding for this work comes from the National Science Foundation via a career award. So we're very thankful for that. And thanks for listening to our poster.